All right, guys. So implicit differentiation. It's a really fancy name for taking a derivative. All right. So right now, you guys have been doing derivatives since the, May of your junior year. You did a little bit of derivatives. We've done them all this 9 weeks so far. You have been doing derivatives with explicit functions or explicit equations. Explicit equations mean equations that are solved for one variable in terms of another. So it's always been y equals, hasn't it? I mean, every one you've done, it's been y equals or f of x equals. Those are what we call explicit relationships because you are defining y explicitly in terms of x and other stuff, right? Well, implicit doesn't necessarily have to do that. Implicit, just grab a different pencil. Grab a different pencil. There's a whole stick right there. Should be. All right, so implicit has maybe x's and y's on one side, x's and y's on the other side. It might have x's and t's, w and t's. I can even get into the realm of like, you know how in chemistry you learn that pressure times volume? Dude, this just light me up. Okay, you remember how you learned that pressure times volume equals N times R times temperature, right? And there was that relationship. That is an implicit equation. It's got variables all over the place. We need to learn how to take derivatives of those. So I am going to tell you that I have been withholding information from you. You don't even know it, but you literally have been doing it, not knowing it. So for instance, can somebody tell me why on earth, when I have an equation like y equals x, why is the derivative of x 1 and the derivative of y dy dx? Why wouldn't they both be 1? I mean, does math really understand the difference between one variable and another variable? I mean, how does it go, wait, x? Math is math, okay? And the reason why is this. What I am really doing when I have an equation like this, okay? When I have an equation like y equals x, what I'm really doing is going, the derivative of y is 1 times the derivative of y with respect to x. The derivative of x is 1 times the derivative of x with respect to x. But what's dx dx? It cancels. And all I have left is 1. And what's 1 times dy dx? Dy dx. And that's why when I take the derivative of this, I get the derivative is equal to 1. Now, Newton, when he came up with calculus, always wrote y prime. Leibniz, the other guy who kind of came up with calculus on a different country at the same relative time, he used this notation, which I think is much better. And your book doesn't use it as much as they probably should, but we're going to try to use it a ton. Okay? So the bottom line for you is this. Every single time you take a derivative from here on out, do the derivative just like you would normally, but tack on either a dy dx or a dx dx or a dt dx. But if it's a dx dx, don't bother. So for instance, if I gave you this problem, if I gave you something like y squared equals 3x squared minus 5x. To take the derivative of that, you're going to do just like you would always take a derivative. You're going to say 2y to the first, but then you're going to tack on a times dy dx. When you take the derivative of 3x squared, you're going to go 6x. And technically, you would tack on a dx dx, but what's dx dx? 1, so you're not going to bother. And then you're going to come over here and take the derivative of that, and you get what? Minus 5 times, technically, a dx dx, but since that would cancel, you're not going to bother. And then, since the problem was actually find the derivative of y, the question was probably, what is dy dx? You're going to go, well, to find dy dx, what would I do? You'd go back and divide everything by a 2y. So your derivative of y with respect to x actually ends up being this fraction. Okay, that's a great question. We are normally always taking the derivative of a function with respect to the axis. So if my axis is an x-axis, it's always d dx. You will very soon get to where, related rates is all about how things change over time, and your axis will be time. So instead of dy dxing, we're going to, or instead of ddxing, we're going to ddt it. Now, if I do this same problem and said, hey, what's the derivative with respect to t, then I'm going 2y dy dt. And then I'm going 6x, what? Dx dt. I would have to write it then. Are you with me? Because it didn't cancel. And then I would say minus 5 dx dt. So I would actually have to say that. That's what we're going to be doing when we get to related rates. We're not going to get that complicated. We're not going to be mixing up 1, 2, 3 variables today. But you would have to do that if there were all kinds of variables, like that pressure, volume, temperature equation. The N and the R, I think, were constants, right? But the other ones were things that moved in chemistry. Or if you're dealing with finance, or if you're dealing with all kinds of situations that we'll look for, those things that are related, like pressure and volume and temperature, are related. They're related, and we're going to look at the rates at which they change, not just the amounts and how they change. And that's all about rates of change, which is what a derivative is. But the bottom line is we're really not doing anything different. So if you go back to where we were, I'll give you a couple of examples right here on this page. We learned that derivative of 4x cubed is 12x squared. Well, it's going to remain 12x squared even when I tack on a derivative of the x with respect to x if I ddx it, because the ddx cancels. So why would I bother writing it? But if I take the same 4x cubed and I make it 4y cubed, but I'm still ddxing, then after I do the 12y squared, I take the derivative of the y with respect to x. That doesn't cancel. I got to leave it there. Right here, if I had the derivative of 4t cubed with respect to x, ddx that, well, I'm still going to get 12t squared, but I got to remember to take the derivative of that t with respect to x. And what if I took 4t cubed and told you to ddt it? Here I ddx'd it. So at the end I went dt dx. Here I would go what? 12t squared times what? dt dt. Well, I don't need to bother that. You with me? So we're always at the very end of the day, after we take the derivative using the same rules you already know, we're going to go, all right, I did this. It's basically the chain rule, if you really think about it. I'm going to go back at the very end and go, take the derivative of that t with respect to that t. Oh, wait, that cancels. And if it cancels, I don't need to bother. But right here, after I do the 12y squared, I'm going to take the derivative of that y with respect to that x. And if it doesn't cancel, we leave it. Are y'all with me? Okay, practice makes better. So let's kind of move down one. Here, quick, some examples. The derivative of x plus 3y. So what's the derivative of x? 1 times what? Derivative of x over dx. Well, that would have canceled, so I don't bother writing. Then I go plus. Now I take the derivative of 3y. What's the derivative of 3y? 3 times what? The derivative of the y over the derivative of the x. That doesn't cancel. Leave it. Jump over to this one. What do you see here? Ooh, product of two things. Looks like a product rule is going to be in play. So you got to know how to do these, so lock in. If you see a product of two things that we have to take a derivative of, I'm going to go first, write it down, the derivative of the second. What is the derivative of a 3y, of a y cubed? 3y squared what? The derivative of the y over the derivative of the x. And then plus second d first. What's the derivative of the first part? 2 times the derivative of the x over the derivative of the x, which doesn't matter, so I don't put it. And then at the end of the day here, I just clean it up. 6xy squared dy dx plus 2y cubed.
you said like on the AP test you don't have to simplify, right? That apply to your test as well.
Well, again, no, I'm going to probably ask you to clean it up, but I mean, well, that's on the free response questions. This would have probably been something like a, actually, that probably would never have asked you this. It would have been something different like we're about to do in a second. But it'll probably be a multiple choice question on an AP test. But you never know. What about this one? A lot going on this, right? Now there's 1, 2, 3, 4 parts. There's not a product rule. They're all added or subtracted, so we just do them independently. What's the derivative of y cubed? 3y squared times the derivative of the y over that dx. How do you take the derivative of 3y squared? 6y times the derivative of that y over the derivative of that x. Minus, how do you take the derivative of the negative 5y? Negative 5 times the derivative of that y over the derivative of that x. And then finally, how do you take the derivative of negative 2x cubed? Negative 6x squared times the derivative of that x over the derivative of that x, but those would cancel, so it doesn't matter. And how would this look different, guys? How would it look different if instead of ddxing it, I ddt'd it? Would that part be any different? No, I would just have what? dy dt. Would that part look any different? No, I would just have what? dy dt. Would that look any different? No, I would just have what? dy dt. Would this look any different? Yes, what would I have? I mean, well, the negative 6x squared wouldn't, but you would have what? Times dx dt, because it wouldn't have canceled. But we're not going to get into DDTs today.
So what if,
Well, I guess we just did, but I'm not going to give you any work on those. Yes.
so say the 2x minus 3, or the back part wasn't there. Could you factor out the dy dx?
We're going to, well, I could, but what's the point? Because here, I'm not trying to solve anything. I was just asked to take the derivative. But when I'm asked to find what is dy dt, and you've got a bunch of them, you're going to see I'm going to factor it out so that I can solve, kind of like that example I showed you a second ago. But we're about to do that. Okay? So we've already done a number of these. I'm going to jump down and just get through some of these problems so we can get some better practice. Okay, so see if I can. Dang it.
It's not related to class. But
No, let's focus. So right here, I want to take the derivative of this, right? Given that that is my equation. Now, this is no longer an expression. This is an equation. So obviously, whatever I do to one side, I got to do to the other. And also, the question said, what is dy dx? So as you're doing this, you're going to notice that as we're going through, there's a whole bunch of dy dx's that are going to show up in my problem. I'm asking you to solve for them. So if you see a bunch of them, like Ella mentioned, what you're going to want to end up doing is factoring them out, and I'll show you how to do that, dividing everything else away so you have nothing in the end but a dy dx equals. So let's just get started. What's the first part? The derivative of y cubed is, and I normally do this. I normally ddx both sides. So I'm going to ddx the left, and I'm going to ddx the right. And you'll see that in my key usually in all of my problems. So what is the derivative of the y cubed with respect to x? 3y squared times what? The derivative of that y with respect to x. Move on. The derivative of the y squared, 2y, dy dx. The derivative of the negative 5y, negative 5, dy dx. The derivative of the negative x squared, negative 2x, technically dx dx, but that cancels. And then finally, what's the derivative of that constant? 0. So you've done the derivative correctly. Now your goal is to find this. And don't go, there it is, right? I mean, to find it, we want to isolate it and solve for it. So right here, I can look at this and I see there's a term, another term. There's 3 terms that have a dy dx, one that doesn't. Take everything that doesn't, move it to the other side. Or whatever you do, get all your dy dx's on one side. So I'm going to leave these here. I'm moving that over. Now, when I move that over, can everybody see that that gives me negative sorry, positive 2x over here when I move it over. Are you with me? Yes? I'm trying to avoid taking a whole other step and copying this again. So I'm moving this to this side. Now I have that equals this. Then in my next step, I'm going to factor out the dy dx out of everything, leaving me 3y squared plus 2y minus 5 in parentheses or brackets or whatever you want to do. It doesn't matter. You with me so far? And then I'm going to divide all of that on both sides. Now that cancels, and I have dy dx, which is 2x over 3y squared. Now, what's different about this derivative than other derivatives? There's two variables in there now. So normally when I was taking the derivative, all I needed was the x coordinate, right? Now when I take the derivative, I need the x coordinate and the y coordinate. So if I told you, hey, take the derivative when x is 2, and by the way, this is how you'd write that. If I said take the derivative when x is 2, you go, well, if x is 2, I'm going to need to know what the y coordinate is that goes with it. How would I find that? I come back, plug it into the original equation right there, plug it in there, and solve for your y. And by the way, I wouldn't make you do that on this one because that would be terrible. Actually, no, because that's -4. So that's going to cancel and leave you a 0. And then, yeah, you could factor y out and use the quadratic formula. So actually, you could do it here, but there were three. You end up with 3 different points. But we'll do one of those in a second. But the bottom line is, I need to know that y coordinate so I can plug stuff in for x and for y. So if you need it, go get it. But normally, you don't have to work that hard. But I will tell you, I have seen AP questions that were not kind in that regard. And I'll throw a couple at you that aren't super kind in that regard, too. But we didn't have to do that here. We could stop right there. All right, what about this? Find the derivative of y with respect to x given that implicit equation. Gosh. Giving up on that. Okay, so ddx both sides. I'm going to ddx the left, and I'm going to ddx the right. And by the way, I don't dy dx the left. The y is kind of like that. So I'm taking the derivative of that with respect to x, the derivative of 0 with respect to x. So what's the derivative of the first part? What do you see right here? Good. Product rule. So here we go for just this part. First times the derivative of the second. How do we take the derivative of an e to the blah? E to the blah times the derivative of the blah, which is 1. dy dx. Good. That's first d second plus second e to the y times the derivative of the first. What's the derivative of x? 1 dx dx, so just 1. I'm going to put a 1 just to show you I did it, but I wouldn't even bother. So this is first d second plus second d first. I've done the product rule part. What's the derivative of -10x? Just -10. I don't need dx dx. And what's the derivative of 3y? 3 dy dx. And then finally, what's the derivative of 0? 0. Now, what do I do next? So this term and this term have dy dx's in them. Move everything else over. So I am going to subtract the e to the y from both sides. I'm going to add 10 to both sides. And that's going to move both of those over, right? And then to save a step, I'm going to take what's left and do what with it? Factor out the dy dx. And what would I have once I factor it out? X e to the y plus 3. And then, so I should be able to do all that in one step. And then the last thing I do is divide by whatever is being multiplied by dy dx. Canceling all of that and getting dy dx. And again, you can see that for me to do this derivative, I would need to know the x and the y value at that. So I don't just need an x value anymore. I actually need a point. But I didn't ask to do that, so you're good.
Are we gonna do another supplement?
Sure, it's coming up. Oh, yeah, I mean, it's coming. All right, what about number 7? Ooh, number 7. What's that?
The second derivative.
Second derivative. Can you magically jump to the second derivative? No, so you're going to have to do the first derivative and then do the second derivative. Now, something curious happens that you got to remember to do, but I'll show you, and it's kind of clever. So check it. Check it out. So the first derivative, I'm going to go ahead and ddx it. ddx the left and ddx the right. So help me get started. What's the derivative of x squared? 2x. That's all I need, right? The derivative of y squared? 2y dy dx. And the derivative of 36? 0. So to solve, I'm going to move over the 2x. Nothing to factor, which is kind of nice. That gives me a negative 2x on the right. Divide by a 2y. Cancels that out. And I get dy dx equals negative x over y. And I'm going to tell you, it doesn't really matter where that negative goes. But I like putting it in the numerator. And let me tell you why. It's technically on the outside, right? Because I subtracted it. You think about that. But when in a second, I'm going to do the second derivative, right? And the second derivative is going to make me do what with this? Low d high minus high d low over low squared. You got an option. You can either leave the negative out there, put a big parentheses, go low d high minus high d low over low squared, and then multiply the negative in. Or you can just make the negative be with just the top part. So when you do low d high, it's already been assigned to either the top or the bottom. I like that. So I like to assign that negative to either the top or the bottom, doesn't matter. And then I'm going to start my process again. Now, if that's the first derivative, what do you think you do to find the second derivative? I ddx both sides again. So I'm going to ddx the left and ddx the right. Now, this is why you end up getting d squared y over, it kind of looks like it's saying dx squared, but it's really dx, quantity squared, because there's 2 dx's. It's just mathematicians don't write that. They just write dx squared, because they just assume everybody knows. But it would probably look a little bit better if they did this. d2y over the quantity dx squared. It would look better like that, but it's just not going to be written like that. So deal with it, I guess. Blame Leibniz. Now, how do I take the derivative of this fraction? So here we go. Low. See that the negative's already assigned to the top part. D high, what's the derivative of the negative x? Negative 1. Minus high negative x. What's the derivative of the low? 1 dy dx or just dy dx? All over the low squared. Now, here's the part you got to remember to do on a second derivative. You know how they tell you in English, you never define a word using that actual word? Like I would never say that beautiful is something, a characteristic we use to describe something with great beauty. Because I'm still clueless, right? If I don't know what beauty is. Well, I'm not going to define a second derivative in terms of a first derivative. I'm not going to say that the rate of change is equal to blah, blah, blah rate of change, because I still don't know what the rate of change is. Oh, but wait, I do know what the rate of change is. What is, in the blue, look back, what is dy dx? Negative x over y. So I'm going to replace dy dx with negative x over y. So here we go. Negative y, negative x is plus x times negative x over y, all over y squared. Now, if it were me and it was a free response question on the AP test, you could leave it like that. But if it's a multiple choice question, which more than likely this would be, that's probably not going to be an option. So what would you do to simplify? There's a little trick I have taught many, many people before and shared with you. Multiply the top and the bottom by whatever the common denominator of everything was. And the common denominator of all this is what? Y. So if I wanted to, one option, I'll do it right here. Is over y squared, is to take the entire top and the entire bottom and multiply it by y over y. And that gives me negative y squared. And that this times this is going to cancel and give me just a negative x squared. And on the bottom, I get a y cubed. Your other option is just to stick with what you know and go, well, and this is going to be a little messy. I'm going to do this over here. I'm going to take that blue part, come over here and go, well, you could go negative y minus x squared over y. And then you could say, well, I need a common denominator. So to add a y over 1 to this, I would need to put a y on the bottom and an extra y on the top. And that would give me negative y squared, negative x squared over a y, all over y squared. And how do you divide by y squared? You multiply by the reciprocal, 1 over y squared, and then that gives you that over y cubed. Are y'all seeing that? But don't forget on the second derivative to plug it back. You never want to leave that in there. But because of AP rules, you're allowed to just plug it and leave it. It's a free response question. All right. Now, this is going to take a little bit of time. I don't know if we'll have time to finish. We're going to do the best we can. But this says, it's a common AP question. If we don't finish it, we'll get back to it later. But it said, find the points at which the graph of this equation has either a vertical or horizontal tangent line. Now, stop and think for a second. What happens if a graph has a vertical tangent line to it? That vertical tangent line has what kind of slope? Has an undefined slope? Haven't we been just finding slopes? Hasn't what we've been doing today been finding dy dx, which is slope? So what if I ended up, think back to what I just had before. I had, what was the original derivative? Wouldn't it dy dx equals negative x over y? The original derivative, not second derivative, derivative. So if that was my derivative and I said, hey, where would the graph have a vertical tangent line? Vertical tangent lines have undefined slopes. What does that mean to you? That means the slope, how does the slope become undefined? When the denominator is 0. So you would go, oh, well, the denominator is 0 when y is 0. Then I have undefined slopes. Could be, yes.
Like you would just take the derivative of that implicit function.
But make sure you make the connection that it's it's d and e, right?
Yeah.
And then if I say, where do you have horizontal slopes? What do you know about horizontal slopes?
The slope is 0.
When the slope is 0, when would a slope be 0 if it was a fraction or anything?
X is 0.
When the top is 0. So where the slope is 0, you take the top, set it equal to 0 and solve. Well, you're not going to get a simple slope in this one. I mean, take a look at it, right? So I'm going to move kind of quickly through here to help you see it. But here's me taking the derivative first. Derivative of that, 8x. The derivative of that, 2y dy dx. The derivative of that, negative 8. The derivative of that, 4 dy dx. The derivative of the 4, 0. The derivative of the 0, 0. Then I move these two things over. So positive 8, negative 8x. I factor out the dy dx out of whatever's left, which leaves me 2y plus 4. And then I divide by a 2y plus 4. Are y'all seeing this, what I've just done? Now, this is my slope. Anywhere on the graph. So if my question is, find the points where I had a vertical, we'll start with vertical. Vertical tangent line. What do you know about vertical tangent lines? Undefined slopes, right? Where do I have undefined slopes? Where what? Where the denominator is 0. So all I have to do is take my denominator. So therefore, that's what the little 3 dots means. It means therefore. Take the denominator, set it equal to 0, and I find that y is -2. Now, is y equals -2 a point? But I'm halfway there, right? Actually, way more than halfway there. So if I want to find the points, I go, well, my points have a y coordinate of -2. How could I possibly take this y coordinate of -2 and find which x went with it? Plug it back in the original. Now, as bad as that looks, just do it. So 4x squared plus y squared, which would be plus -2 squared, that's a 4, minus xy, sorry, minus x, 8x, plus 4y, plus 4y is 4 times -2, plus 4 equals 0. So what do I end up with? This -8 cancels with that 4 and that positive 4. I end up with 4x squared minus 8x equals 0. Can you solve that? Factor out of 4x. And I get it 0 and 2. So my points are when x is 0, I get a y of -2. And when x is 2, I get a y of -2. So those are my points. Where it's what? Vertical tangent lines. Sweet. What would I do differently to find horizontal tangent lines? Take the numerator. And so I take the 8 minus 8x and set it equal to 0. Y'all seeing that? The bell's about to ring, so. Hey, do what you can. Please don't skip out of this homework. And guys, remember, what's the definition of insanity? Doing the same thing and expecting different results. If your style of studying is wait to the last minute and you're getting A's out of it, great. If you're not and you want improvement, quit doing that. Keep up a little bit better. Come see me a little bit more. All right, hey, y'all, great weekend.
Harry, I've had you for 2 years, maybe however long at this point. I didn't know the 3 little dots meant therefore until